This video is our first in a series about chemical kinetics. And chemical kinetics are about not just what's happening in the reaction, but how fast the reaction is happening. So today we're going to look at a general way that we describe the rates of reactions, and then also some factors that will influence the rates of reactions in a kind of a qualitative way. We're going to get into a lot more detail in future videos. Reaction rate is the basic way that we describe how fast reactants become products or how fast the reaction is moving. So one way we can think about this is by looking at the change in concentration over the change in time, which is basically what reaction rate is. So imagine we have this generic reaction of reactant A and reactant B, 1:3 ratio, creating product C. So B and C aren't boron and carbon. These are just meant to be generic placeholders for real chemicals. This is what a graph of concentration versus time might look like as the reaction proceeds. At first, the concentration of A and B will be quite high because they're reactants, and the concentration of C will be essentially zero because there isn't any until the reaction starts producing C. As time goes on, the concentration of A and B will both drop, but the concentration of C will rise. And by looking at how fast those changes are taking place, we can express the rate of this reaction. One way that we can do that is with something called the average rate. The average rate is just kind of over the long stretch of time, how much is the concentration changing. We could think about this graphically as a slope of a line that just connects the beginning and the end of our time segment. We can think about this mathematically as the ratio of the change in the concentration over the change in time, which is just how you would express the slope of that line. For B, we would also have an average rate, but it's going to be different because the slope is going to be a little bit different, and it's the change in the concentration of B with respect to time. Notice that these are both negative, the slopes are negative, and that's because we're losing A and B. For C, however, the rate's going to be positive because we are gaining C, and we're seeing a positive slope on the line. Another way we can think about rate is not as an average, but at a moment in time, at an instant in time, what is the rate? Here we have to think about this kind of using calculus notation. Instead of thinking about delta B over delta T for B, for example, we would think about dB over dt, which means what is the slope when the difference between the beginning and the end point drops to basically zero. So we can also think about this graphically as a tangent line. So at the very beginning, the tangent line to that B curve would have this slope, and that's the instantaneous rate at that time. Later on, that slope is going to decrease. If we pick an instant in time that's a little bit later on, we see that slope decreasing. And the farther we go on, the more that instantaneous rate is dropping. Another way of thinking about rate is the initial rate. The initial rate is an instantaneous rate. It's just the rate at the very beginning. So for A, that would look like this. That's the tangent to the A curve at time zero. For B, it would look like that. And if you notice, the slope of B is about 3 times steeper than that of A. For C, the initial rate, or the instantaneous rate at time zero, is positive, and you'll notice that it's about double the steepness of the slope of A. The rates of A, B, and C are all related to each other by stoichiometry. So because the coefficient on B is 3 and the coefficient on A is 1, there's a 3-to-1 mole ratio between B and A. So the rate of B is going to be 3 times the rate of A. The rate of C is going to be -2 times the rate of A, and that's because the ratio would be a -2-to-1 ratio because C is a product, so it's going to have the opposite direction of slope as the rate of A, which is a reactant. So we can just use mole ratios once we know the rate of one reactant or product to find the rates of the others. What are the things that will influence reaction rate? Well, one is that some substances just react faster than others with a given reactant. For example, if I put some magnesium in 6 molar hydrochloric acid, in less than a minute, that piece of magnesium is going to be completely gone. There'll be a violent reaction and a lot of bubbles of hydrogen will be produced. If I dropped a piece of aluminum in 6 molar HCl, the reaction will produce hydrogen gas. There'll be some bubbles, but it'll be much slower, and it'll take several minutes, maybe even an hour, for all the aluminum to disappear. Another thing is surface area. I would encourage you to look at this video here where some students are trying to light gasoline on fire in a very cold environment. The reason that it doesn't really work very well until they heat up the gasoline is because not very much gasoline has evaporated. It's in the liquid state, and so the individual gasoline molecules can only interact with air to combust at the very surface. But once you allow them to evaporate so that they're surrounded by air particles, the reaction rate goes much more rapidly. The reason for this has to do with the ability of the reactions to interact. And if we think about this with a kind of a generic simple cube here that's 1 centimeter on a side, the surface area of this cube, 1 centimeter on a side, each face is 1 centimeter by 1 centimeter, so that's 1 square centimeter, and there's 6 faces. So this cube has got 6 square centimeters of surface area. The surfaces are the only place where this could interact with another reactant to cause the reaction to occur. But if we had the same volume of this, whatever this substance is, and we divided it into pieces so that each one of these little tiny cubes was 1/100th of a centimeter on a side, well then the surface area of each one of these little cubes would be 0.01 centimeters squared, which is 0.0001 square centimeters. And there's 6 sides, so each one of these little cubes would have a 0.0006 square centimeter surface area, which is really small compared with the original cube. But don't forget that we have 100 times 100 times 100, or 100 cubed of these little tiny cubes. So when we put that all together, now we have 600 square centimeters, 100 times more surface area. And so smaller particles give more surface area gives a faster reaction. And this is responsible for things like dust explosions that occur very rapidly, or that's why we see all combustible substances burn at much faster rates when their surface areas are increased, when they're ground into smaller particles. Another factor that influences the ability of reactants to interact is the concentration. If the concentration of one of the reactants is higher, then that means there's more particles for the other reactant to interact with, and so the reaction rate will go faster. For example, if I take a piece of copper and I put it in some 18 molar nitric acid, that piece of copper will be gone in seconds. It'll interact and produce a gas, copper ions, and I can do the same thing in 6 molar nitric acid, lower concentration, but it'll take around a half an hour. I have a piece of copper that I put in some 2 molar nitric acid, and that reaction has been going for over 2 decades, and the piece of copper is still partly there. So concentration, increased concentration, increases the reaction rate just because the particles can get together better. Another one is temperature. If the particles are moving faster, which is what higher temperature means, that means they're just colliding with everything more often, and that means they're colliding with each other more often, and that means their ability to interact is increased. So reactions that occur at higher temperatures typically go faster than reactions that are going at slow temperatures. And there are lots of examples of this in real life. That's one of the reasons that we cook food, for example, or one of the reasons that we put food in the refrigerator or the freezer. By lowering the temperature, the reactions that cause decay happen at slower rates, and so our food can last longer. And then there's another thing called a catalyst. And a catalyst is something that we add to a reaction. It's not a reactant, but it participates in the reaction temporarily in some way. And we'll have a lot more details about catalysts in a later video. But it increases the rate of the reaction even though it is not itself a permanent part of the reaction. Now it's time to get quantitative about this. How we describe this is through something called a rate law, or sometimes this is called a differential rate law. The general form of this is that rate is equal to some constant number, so that's a constant of proportionality, times the concentration of whatever reactant raised to some power. And that power is called the order of the reaction. So sometimes they're zeroth order, it doesn't depend on concentration. Sometimes they're first order, sometimes they're second order. And we're going to look at how we can determine what that order is, and then how could we use that to find rate constant. So one way we do this is using something called the method of initial rates. So what we're doing is we're looking at here 2 experiments where we have one reactant, A, just a generic reactant. Its concentration is measured in moles per liter, and the rate is measured in moles per liter per second. So that's a change in concentration, a change in moles per liter every second. We have 2 different experiments. In the first one, we started out with a concentration of A that was 0.10 moles per liter, and the initial rate was 0.2 moles per liter per second. In the second one, we started out with a higher concentration, a 0.2 molar concentration. The initial rate was 0.4 molar. First of all, I'm going to do kind of a rigorous development of how we can determine the order, and then I'll show you a little bit of a shortcut that you can often use. So let's take the first experiment and just write out the rate law. So for experiment number 1, the rate, so that's on the left-hand side here, was 0.20 moles per liter second, and that's equal to some constant number times the concentration of A, but we know what that is. It was 0.10 moles per liter for the first experiment, raised to the n power. So that's from experiment number 1. From experiment number 2, we can write the same rate law. We could say that the initial rate, which is 0.40 moles per liter second, equals K times 0.20 moles per liter raised to the n power. We can solve the second equation for K to get rid of it. So K is equal to 0.40 moles per liter second divided by 0.20 moles per liter raised to the n power. And then we'll substitute back into the equation from the first trial. So that gives us 0.20 moles per liter second equals, now we're going to substitute 0.40 moles per liter second over 0.20 moles per liter raised to the n power, and then that's times 0.10 moles per liter raised to the n power. Now I'm just going to rearrange a little bit. 0.20 moles per liter second divide by 0.40 moles per liter second. So I divided both sides by 0.40 moles per liter second equals 0.10 moles per liter divided by 0.20 moles per liter, and both of those were raised to the n power. 0.2 divided by 0.4 is 1 over 2. 0.1 divided by 0.2 is 1 over 2, and that was raised to the n power. Okay, so 1/2 raised to what power would be 1/2? Well, obviously n is 1. Now you could take the log of both sides if this wasn't so simple and solve for n, but here it's quite obvious that the only way you're going to get 1/2 by raising 1/2 to something is that something has got to be 1. So that means the order of this reaction is 1. So the rate law is rate equals K times concentration of A raised to the 1 power. Now, if I wanted to find out what K was, now that I know that N is 1, I can just grab either of these equations, plug in a rate, plug in the corresponding concentration, and solve for K, and then I'd have my K value. Okay, now I'm going to show you the shortcut. Somehow this label got displaced. That belongs up there. Let's look at what's happening here between experiment 1 and experiment number 2. The concentration of A naught, the starting concentration of A, went up by 2 times. What happened to the rate? From here to here, the rate went up by 4 times because 1.2 is 4 times 0.3. So rate went up by 4 times. So 4 times increase equals a K times 2 times increase raised to what power? So this is a kind of a shortcut. 2 raised to what gives me 4, 2. So that means that this is second order. So the rate law here would be rate equals Ka to the 2 power. Now you can do the same rigorous thing that I did by doing all the derivation, substitution, and everything, and you will arrive at the same conclusion. Sometimes you have to do it kind of the hard way, but lots of times you can do this little shortcut. The important thing is if you are asked to show a rate law from something like this, even if you take the shortcut on an AP test or on a test that you're doing in my class, you're going to have to explain how you did it. So you think about how you're going to explain that in words. And if that's hard for you, just do the math. This can work when you have multiple reactants too. So say we have this hypothetical reaction. A plus B are both reactants and they're making a product C. Let's find the rate law. So the rate is equal to K times A to some power times B raised to some other power. You need more experiments to do this, but here they are. In the first 2 experiments, we notice that the concentration of B isn't an issue because it's the same. What happens to the concentration of A? It goes up by 2 times. What happened to the initial rate? It also went up by 2 times. So since the same thing happened to the rate as happened to the concentration, it's first order in A. Now let's find 2 experiments where A concentration doesn't change. So the last 3 all have the same concentration of A. We could use this pair. What happens to the concentration of B? It goes up by 2 times. What happens to the rate? The initial rate goes up by 4 times. So since doubling the concentration quadrupled the rate, the effect that concentration had on rate was a factor of 2. So it's second order in B. Again, you can do the more rigorous derivation of this if you wanted to, but this little shortcut works here for these experiments. And it's also important to note that I didn't have to choose those 2 experiments. I could have chosen those 2 experiments too, and it would have led me to the same conclusion. Our last topic is the general order of the reaction. So we would say for this reaction that's expressed by this rate law, that the order of the reaction in A is 1. It's first order in A. We would say that it's second order in B because it depends on the square of B. But when we add the 2 orders together, we get 3, and so we would say that this reaction is a third order overall reaction. So in case that comes up sometime, you want to know what's the overall order for a reaction. That's how you do it. Find the order of the individual reactant species and then just add them up.